And now we'll carry on talking about aggregate measures, which is a category that includes counters. Counters, as the name suggests, keep a count of events, number of interrupts, number of cache misses, amount of data bytes written, number of calls to function do magic. Keeping track of these numbers is relatively inexpensive, especially when compared to other approaches. So counting every occurrence of an event is actually plausible. And counters are, as I say, an aggregation, because an aggregation is taking a bunch of data and combining it in some way. It's a summary. In this case, we're summing, as in arithmetic sum, the number of occurrence. And at the end of the program, we get a total number, and the total number tells us, hopefully, something interesting. Now, the counter and any data that we derive from it takes a lot less space than the original data, than actually showing the exact executions of this function. If it's all aggregated in the counter just produces a number, and the number is pretty small. And so, yeah, sum is just the simplest kind of aggregation, but others are exactly what they sound like, some other kind of summary of your data. Calculating the average response time is an aggregation. It happens to be based on two counters. It sums up the total time per request and divides it by the number of requests in the given period. And hopefully the resulting value is useful to somebody. Asking the computer to calculate the summary obviously makes sense. It's not super realistic to ask a human to look at 50,000 requests and calculate their average time. It's just kind of inefficient to ask them to do that, and the computer can do it very easily. And some possible ideas, if you wanted to think about some other kinds of aggregate measures: number of requests in total, requests broken down by type, average time to respond to requests, the percentage of requests that return an error response. All of those things are just super quick, off-the-cuff examples of here's a thing that you could use aggregate measures for. And the thing I want to get across, that whatever aggregate measures we use, context is the thing that makes them interesting or useful or have some sort of meaning. As Clara asked the doctor, is for a lot, dollars no, murders yes. Context is actually what makes the difference here. Let me give a computer-related example. No violence required. Suppose that after my pull request has merged, the average login time from a user is 0.75 seconds. Is that good or bad? Some context helps us to answer that, is good or bad. Without a baseline to compare it to, I'm not sure. If it was 0.75 seconds before, then my PR made no difference. It was unrelated, or it had no effect when I desired some effect. But okay, let's say that for the purposes of the example, before my PR it was 0.5 seconds. So the total time for that has increased. Is that bad? Is that bad? Again, it sounds bad. I mean, we usually talk about can we complete work faster, but that's not the only goal, right? Suppose that I'm intentionally making login slower to make a brute force password attack more expensive for an attacker. Well then, increasing the amount of time from 0.5 seconds to 0.75 seconds is good. In fact, maybe it should be even longer. Maybe it should have been up to 1 second. Context is important, and without the right context, we don't understand the change. Okay, let's take another example. Request takes on average 1.27 seconds. Is that good or bad? Again, context is what we need to know without a point of reference. Are we being asked to approve or deny a transaction and there's a time limit of 1 second to provide that answer? Otherwise, a default is assumed. If that's the case, then yeah, actually this is terrible. We are missing it with the average case, let alone a worst case. What if the time limit is 10 seconds? What if the time limit is 10 seconds? Is that enough? Well, averages, as the saying goes, can be misleading. Right? What if 1.27 seconds is normal, but the maximum time is more than 10 seconds? It's rare, rare enough that the average can be 1.27 seconds, but not so rare that we can just pretend it never happens. What then? Another thing to consider is, how hard of a deadline are we talking about? Like, what happens if our answer is late? If the answer is useless if it's late, then yeah, that's an issue. If the answer is not as good but still has some value if it's late, we might be able to live with it if that's rare. It's really hard to know. So maybe looking at the average is the wrong thing. Maybe we want to look at the maximum time. Maybe we want to look at the 95th percentile kind of aggregate measure instead. Choosing the right ones is important. Here's another way that you could think of as averages are misleading. The burst can be quite different. If our service receives on average 7 requests per second, does it mean it looks like the first, the second, or the third row here? All right, probably you imagine if I tell you that we get 7 requests per second, you kind of imagine that in each second we get 7 requests, maybe a little more, maybe a little less, but not as dramatic a variation as we see in option 2 or option 3, right? That is just sort of our human nature, our human bias. We expect things to be kind of nice and even and pretty, but realistically, life is not like that sometimes. And all of these have 7 requests per second, but only one of them is super predictable and arrives evenly. So later on in the course, we're going to talk about queuing theory, and we'll learn about random arrivals, and we'll understand what it means for things to arrive, and what even really is a random arrival. But just keep in mind when we think about counters and averages and what have you, that sometimes they don't mean what we think they mean. Another thing to think about in terms of aggregation is choosing a period of time. Right? If we are thinking about aggregating the average number of requests, is that the average number of requests per hour? Is it the average number of requests per day? And if we are saying something like requests per hour, what part of the day are we considering when we look at that? Is it the whole day? Is it a part of the day? It's fairly difficult to imagine, right? Sometimes we have some pretty easy answers. Right? If we're encoding the video, I want to encode the video that's going to get published on YouTube for the lecture on this, right? I'm converting it from the raw form that I've recorded it in into the final version with the edits and the stuff that's been added. And it takes, in the example, 3 hours, 21 minutes to encode, and that results in a processing rate of 210.9 frames per second. Then, that average of 210.9 frames per second is aggregated over the whole execution time of the task, right? The 3 hours, 21 minutes represents the entire execution time of the task, and it makes sense to figure out what is the average frames we could edit during that period. For services that run indefinitely, or just if we're impatient, we probably want to look at a shorter period of time and consider things, right? So if we look at transactions per hour, that might be broken down across, these are the transactions per hour yesterday. Suppose that yesterday is a good day to look at, then we could imagine that's a reasonable time to aggregate. But if we choose the wrong period, we miss important things. If we're looking at purchases per hour, if we look at Sunday, that might actually be misleading because a lot fewer purchases take place on Sunday as compared to a weekday. And if we've chosen the wrong periods, we end up looking at the wrong things and sort of not getting the real picture. Same thing if we choose the whole day or the whole week as a period of the aggregation, we might lose some of the context that says, things are really busy during the workday and they're quiet at night and very little happens on the weekend. So in addition to our counters and aggregations, we need to find a way to show them. So, look at the pretty pictures. Graphs and visualizations really help us to see trends in the data, not just the raw data. Choosing the right visualization is very helpful. If you think about a car, like a digital speedometer, where it shows you the numerical value, is more accurate than one of the ones where the little arm sweeps, in terms of showing you the exact speed of your vehicle. Right? It tells you, hi, I'm traveling at exactly 62 kilometers per hour, and you say, yes, that's very precise, I like it. Whereas the sweeping analog speedometer makes it a little bit easier for a person to understand the acceleration, the rate of change of that speed, right? Because the position of the arm tells you your location, but the speed at which it's moving tells you something about your acceleration, and that's a little easier to visualize and understand and capture at a glance, as opposed to the change in the numbers. Right, the change in the numbers is there, and a computer could probably figure it out really easily, but for a human, it's just not that easy. The other thing that's really nice about these sort of data visualizations is that, well, humans who are not so technical really like them. Managers love seeing the graph. They want to see what happens over time. They want to know sort of what's going on. And showing them this trend of, here's our profits, they like that. With that said, right, there are, of course, limitations to how much you can show, and you will eventually at some point sort of have to trade some amount of detail such that you can fit stuff in the graph. There's no 100% perfect solution. But if we put together enough of those pretty pictures, we end up with a dashboard. And here's a pretty simple example from just my own laptop. When I compile and run the n-body parallel code, the blue represents user space execution and the red represents kernel execution. And you can see at some point we just cap out at 100%. And you can see that's basically where the simulation really starts running for real. There's opening the editor, and there's compiling it and what have you. But when the simulation actually starts running, the CPU goes to 100, and it just continues unabated until we say that we're done. Now, dashboards are ideally a little bit more than just pretty pictures of line goes up. A dashboard is really intended to be a collection of useful graphs, time trends, histograms that present some summary of the situation, ideally something that you can easily digest. Good dashboards make it clear what's happening and what things need attention. Of course, dashboards also make more sense when we have many things to measure. They're not as great if we're just trying to optimize for one specific thing. So all of this discussion around a very high level of profiling and tracing and what have you is just identifying what's happening and what operations, if any, are slow or at least slower than expected. Once we know that, for example, importing CSV files with tax rates is slow, we could use some lower level profiling tools to identify what's slow inside that particular functionality. And really, as we go through the next couple of topics, we're going to sort of narrow down a little bit about what area is the bottleneck, why is this the area that we think is causing the problem, and then we will identify some very specific things. Is okay, we should look at this function at the lowest level as something we want to change. So we'll pick up in the next topic by trying to identify what is the area of the bottleneck. Is it CPU? Is it something else? We'll find out.